Hello, everyone, and thank you for joining us in our next session, all about heat pumps, which is quite a topical story these days. So good thing we've got an expert joining us to tell us more about it. I've got Thomas Lergenmueller today, who's going to be telling you more about, well, giving us an introduction to heat pumps. He's got quite the impressive CV. He's the product manager for heat pumps at GEA Heating and Refrigeration Technologies. And since 2015, he's been responsible for the product management and development of package components within the Heating and Refrigeration Technologies division. Quite a mouthful. Prior to that, from 2008 to 2015, he was responsible for the product engineering and development of package components. And he graduated from the University of Berlin, the Berlin University of Technology, with an MS Mechanical Engineering, wow, and from the Stevens Institute of Technology in Fordham University in the US, with a master's in management. So definitely the right person to be talking. So before I hand over to Thomas, just a few housekeeping issues. If you want to send through a question, please make sure you're logged into the event platform. There's a Q&A button on your Zoom at the bottom. We'll be taking the questions at the end after Thomas has been giving his presentation. And also, if you want to actually ask the question yourself, you can click the raise hand button, and then I'll unmute you later to actually ask the question from your side. But yeah, I'm sure everyone's going to say it a million times, but without further ado, Thomas, over to you. Thank you so much.
Okay. I hope everybody can hear me. Yeah, it seems okay. And I hope everybody can see the screen and the first slide or the introduction slide. So yes, thank you for this very kind introduction and the opportunity to present or to give a short presentation about our heat pumps, the sustainable and future-proof solutions for industries and communities. I guess everyone who's listening in has a heat pump, and I'm not talking about those who own houses, but those who actually have a fridge in their kitchen. Yeah, heat pumps, there are devices that transport heat from a lower to a higher temperature level, and fridges in the kitchen, they are refrigeration devices. They are producing heat as well. Therefore, they are heat pumps. Yeah, and every refrigeration cycle ultimately produces more heating energy and cooling energy. And to stay a little bit in this example, or actually to stay in the kitchen and look at energy management that's maybe not optimal. Let's suppose you are firing your oven with coal, gas, or any other faucets, and you're leaving the flap open while baking or while cooking. And then you think of installing a air conditioning system because it's getting too warm in the kitchen. That, of course, also produces heat on the other side, which is bigger than your cooling energy. Why this example? Because you can basically transfer this concept or this idea to factories where still you see a lot of non-efficient and non-sustainable generation of heating and cooling energy. There's air conditioning, there are refrigeration devices, and then your oven typically, of course, that's any heating device, a classic boiler, for example, again, fired with coal, gas, oil, any fossils that, of course, eject or emit that CO2. So let's start with a short introduction, a little bit the basic know-how and the global relevance. You've seen this example here of this factory. And of course, we want to do it better. And how does it work? How does the heat pump work in this context? A heat pump can you need a heat source. And you can take, for example, waste heat from cooling devices, from refrigeration plants. And this is, you can use that in your heat pump. This is going into the heat pump and lets the refrigerant evaporate due to the heat transfer. And then the refrigerant is compressed to a higher temperature and pressure level, where it then condenses. And while liquefying, it rejects the heat to a heating cycle that provides any heating demand there is in the industry, process heat, facility heating, that is called the heat sink. And after the refrigerant has liquefied and rejected the heat to the consumers here, it is expanded again to the lower pressure and lower temperature level, where it can evaporate again, and then the whole cycle starts anew. So here, this is an example where this heat pump sucks up waste heat from industrial processes, from air conditioning, cooling devices that also emit heat. If you don't have that kind of heat sources, heat pumps, or our heat pumps, obviously, they can use different heat sources from the environment, for example, any liquid from the environment, from river, seas, waters, there's wastewater, brackish water, sewage water, or you can directly connect a cooling system to the heat pump. Then you kind of have a simultaneous cooling and heating device. So this is a single stage, the principle of a single stage heat pump. It is fired by, or it's powered actually by an electric motor typically. And even if you do not have electricity that is based on let's say green resources, if you do have an electric mix, a heat pump is always a lot more sustainable than classic heating devices based on fossil fuels. Why? If you have a classic boiler, and you inject one energy unit, so to say, you are receiving 80% of it. The efficiency of typical boilers is 80%. So 20% of kind of the energy that you're supplying to it, it's just lost. So your efficiency 80%, meaning you're getting 0.8 units in return if you input 1 unit. If you do the same with a heat pump and you have 1 unit of electricity, you're being provided between 3, 4, 5, maybe even 6 units of heating capacity. That's possible because, as we've seen before, the heat pump uses heat from heat sources already. So this is kind of your balance sheet of a heat pump. And this heat that's coming into the heat pump, that's free of charge. It doesn't waste or use any resources. That needs to be available. So if you want to have the same output with a classic boiler with gas or oil, you need to put in 6 units of energy, and then you still don't end up with the same amount of heating rating that your heat pump, your compression heat pump, is able to provide. So this is an important balance, of course, how efficient a heat pump is, how many units of heating energy basically you get per unit of input power, electricity. That depends a little bit on the temperature level, but the relation that is expressed by the COP, the coefficient of performance, which is basically the heating rating, your heating energy divided by the input power, the energy that you have to supply, the electricity in this case of our compression heat pumps. That COP, this ratio, is typically between 3 and 6, somewhere in there, depending on the temperature difference and the temperature lift. So altogether, of course, those devices, those heat pumps, they do have a big relevance for the world climate, both on a commercial level, in the area which we are not active, but foremost also in the industrial level. And this is where we come into play. Of course, climate protection, environment protection, this is this is very different sided, of course. You cannot concentrate on a single things. There's you have to protect the forest, you have to protect the fauna, and a lot of different things. But of course, greenhouse gases are an important contributing factor, and the CO2 is one of them, or actually the dominant one. And if you see the development of the concentration of the CO2 in the atmosphere, you see that really dramatic increase in this super short time. If you look at the history of the Earth, in this super short time of 150 years, or just a little bit more, how this concentration has risen. And this is a factor, this is a parameter that, of course, needs to be tackled. And if we then look at where all the energy comes from, or how the energy is set up, then we see that 50% of the total global energy end use is coming from the heating. And this heating is still mostly provided by fossil fuel devices. When I say mostly, I'm saying over 90% probably still. That's an estimation from the EU based on a few years ago. So we still have 90% of this large energy chunk which is just provided by burning a lot of fossils and creating the situation that we see here in the chart. Yeah? So in the end, because of that large significance of the heating energy and the fossil devices that are still in place, heat pumps, they are a key technology for decarbonizing the heat generation. If we saw the process, that the device of the heat pump, I was mentioning a refrigerant that evaporates and sucks up the heat, and then it liquefies and it rejects the heat. So that's the key functioning of any refrigeration and also the heat pump cycle. And speaking of refrigerants, we as GEA, we have a long history with ammonia from the cooling, the refrigeration segments. And we are also using ammonia with our standard heat pumps. Ammonia is a natural refrigerant that creates zero emissions. So the so-called GWP, the global warming potential, is zero. It is a very, it's also a very available refrigerant. Only the smallest quantities are used in refrigeration and heat pump systems. All the units, our units, they include a lot of safety, special devices, comprehensive safety chain against excess pressure. So it is a very safe, the way we are handling it. It is a very, very safe thing to do. And after all, this is also a big leverage here, the refrigerants, to ease the situation on the global climate. Because if we do not reduce the use of harmful refrigerant, then this can stimulate 0.5% of the global warming and up to 25% of all the CO2 emissions within the next 25 to 30 years. So using natural refrigerants with a low global warming potential, or ideally with zero global warming potential, helps a lot. It is also very efficient, this ammonia, in our application range. So on top of the ecologic advantages, you also have economic advantages, as we can see in a bit. Here is a calculation with a specific compressor. We are using, or we took a specific compressor size of our compressors. You see the swept volume of nearly 3,000 cubic meters per hour. So it's already a large scale compressor. And we looked at different refrigerants. Here's ammonia on top. Then the second one is still widely used in a lot of regions. And then there are some refrigerants that are typically used for heat pumps sometimes. And we looked at a few figures like the efficiency expressed by the COP, the heating rating. This is the volumetric rating, how many kilowatts can you get per cubic meter per hour, and the global warming potential. Here are values for CO2. So this calculation is based on this compressor size and a heat source inlet outlet of 32 to 25. So basically you're using ambient temperature heat sources, and you're looking to supply heating consumers with a return supply temperature from 70 to 90 degrees Celsius. So these are basically the conditions, the parameters that is the basis of this calculation. And if we do the same, exactly the same calculation for the different refrigerants, we see a lot of different numbers, which there's no need to go through all these numbers. But it's easily, or it's quickly seen that the ammonia in this application range clearly provides the best efficiency, the best COP. It provides the highest rating, the highest capacity. Basically, you can get more out of ammonia, basically, as with different refrigerants. And here's this global warming potential that expresses how much kilogram of CO2 would be emitted into the atmosphere if 1 kilogram of this refrigerant is going to be dissolved. It's leaking or whatsoever. There's a handout. There are handout slides, so you can browse through these numbers. This is not a trick. This is basically pure physics and thermodynamics. But I have to say, of course, with ammonia, we are looking at a certain application range. We're looking at a certain temperature range. We're looking at a certain capacity range with our equipment. That's not saying that outside of this bubble, so to say, that different refrigerants might be maybe even a better choice, considering all different parameters. But we are very convinced, and it's not just us, it's basically a common opinion that in a certain application range, the ammonia really is one of the refrigerants that is best used. The second part, let's have a look a little bit at our heat pump portfolio. So far, we saw how it works, how it can function, how it can be implemented, the relevance due to the global warming and the huge impact of the heating sector, and how heat pumps can decarbonize this energy supply. Now the portfolio will first look at this application range, the temperature and capacity range, which we are talking, which is very useful for ammonia. So let's get you a chart here that's showing the supply temperature and the heating capacity. Basically here, if you're looking at a standard series with reciprocating compressors, piston compressors, we see two fields. Our heat pumps are able to provide temperatures, hot side temperatures between 50 degrees Celsius, and then sometimes we go up to slightly above 80. Some compressor or units can provide only 70 degrees Celsius supply temperature. You see the range from a few hundred kilowatts to 1.5 megawatt of heating capacity. This is not like a straight box. This is not a rectangle shape, but it's like a little bit tilted. It basically just means when you are looking for higher supply temperatures here in the region of approximately 80 degrees Celsius, with the same compressor size and with the same heat source temperature, yeah, your available capacity becomes a little bit smaller, just a little bit smaller, the higher you go in your required supply temperature. So that's basically why it's just a little tilted, these areas. So these are two examples for piston heat pump applications. We have a screw compressor heat pump that's called GEA RedGenium. It provides larger capacity range and temperatures up to 80 degrees Celsius. If we are leaving the standard range and go a little bit more into our customized equipment, then we can provide higher temperatures up to 85 and very large capacities up to 10 megawatt per unit. The capacities are very much depending on the temperatures. I already mentioned that higher supply temperatures means a little bit less available capacity, but the more dominant parameter of your available capacities is your heat source temperature. So this chart here, or this capacity range, is based on ambient heat source temperatures around 30-35 degrees Celsius, or typical temperatures that you see of waste heat from refrigeration plants. So if this heat source temperature drops, let's say you are in a colder region and you are using water from the sea, from the lake, from the fjords, it's often used in the Scandinavic area, then your available capacity becomes significantly less because the temperature drops on the cold side, and that pulls also down your capacity availability range, so to say. There is a new development, which I'm very, very proud about, and we are very excited about this. This is a totally brand new compressor series, a reciprocating compressor series. It's called GEA Grasso VXHP, X for extra high temperature and extra large capacity. So this basically spans now open the temperature and capacity range with a very, very efficient piston heat pump. You can see capacities again up to nearly 2.5 megawatt, and now we can reach 95 degrees Celsius supply temperature. And on a smaller capacity range, if you take the smallest models or the smallest type size here of this heat pump series or the compressor series that's implemented, and you can switch off the cylinders, and with the same efficiency you can still go to part load capacities. So yeah, your capacity range even widens to smaller capacities. So this is a very neat temperature application range that we can serve with our ammonia standard heat pumps. If we're looking at this RedGenium model, this is our standard compressor heat pump. It looks like this. It spans altogether 11 models. So there are different reciprocating compressors included, totaling to a number of 11. They are the most powerful, efficient compressors in the market, and therefore also allow for lowest energy consumption lowest total cost, because your energy consumption, your energy costs, they have a very, very large effect on your total cost. There's a screw compressor counterpart. So basically its sibling, its sister or its brother of this RedGenium is called RedAstrum. This is the same idea, the same design, but based on a screw compressor heat pump. There are 7 sizes in total for this standard screw heat pump. It is a very compact, very low vibrating, and requires very little maintenance with our high-end screw compressors that, like the piston compressors, are also coming from our own development and production for many, many, many decades. We have a combination of a chiller and a heat pump. It's called Blu-Red Fusion. We have a blue chiller line, BlueAstrum and BlueGenium, and we have these 2 red heat pumps, the RedGenium and the RedAstrum. So basically, this is a combination of those 2 modules. Basically, all RedGenium and RedAstrum models are possible in this concept, and this is for very flexible operating modes for high temperature lifts from the heat source to the heat sink for combined cooling and heating. But I have one more slide explaining this idea. And then finally, the customized heat pumps are based on all suitable high pressure compressors for ammonia operation and heat pump operation. And of course, it serves widest capacity and application ranges. Let's have a look at the RedGenium a little bit closer, and to give you an idea of the dimension of how this actually looks like if this was standing in front of you, or if you would be standing next to you. So it's between 4.5 and 8 meters. It's 1.2 meters wide and a little taller than typical human beings. You see here in the middle, this is a reciprocating compressor, I believe with 8 cylinders here. And there's a driveline included, of course. Then it's completed with our GEA Omni controller included in the power panel. So this is completely fixed and ready to start. And here in the back, you see the heat exchanger set that includes some nice gimmicks, a GEA patented solution with a very efficient, compact evaporator-separator combination. On the hot side, it provides a very project individual configuration of each heat exchanger that's also very important for the overall efficiency of the heat pump. So this is the RedGenium, our standard recip heat pump, and the RedAstrum looks very, very similar. Yeah, it's obviously here, of course, you don't have the reciprocating compressor, but here on top sits a screw compressor with the driveline on top of an oil management, an oil circuit. The dimensions are more or less the same. They're moving in the same range. And then it's basically also the same heat exchanger setup here. And of course, the very same controller and power cabinet. So this is the standard. If we have a nice example of something that looks a little bit different and a little bit bigger, this is currently a project in our production, so we don't have final photos yet. This is a computer model. Here you can see just the relation of the dimensions. This is twice the length, the width, and more than twice the height. This was one of the former standard heat pumps, just projected next to this. This is coming from a very large district heating project, 10 megawatts per unit for a district heating network in Finland. Source temperatures are, they have a liquid heat source, probably from a cooling cycle, and they're cooling this down with the unit from 27 to 21 degrees Celsius. And on the hot side, the return temperature is 47, and then the heat pump heats it up to 85, and this is the supply temperature that's going to the consumers. Ammonia charge, I said, we are using really little quantities, which is true for most of the standard units that consume between 30 kilogram up to maybe 90, 95 kilogram. Here we have more than 10 times the amount of in there for 10 megawatts. This, of course, is a different story, and also the weight is nearly 10 times as much as some of these standard units. So these are totally different dimensions, obviously, but it shows very nicely the range of different solutions and heat pumps that we have. Then finally, this chiller heat pump combination, this Blu-Red Fusion. I got one picture, but it's not rocket science. It's a chiller and a heat pump. It's put together. It makes sense to have this in one unit. It's configured as one product, and both stages, the chiller stage and the heat pump stage, are of course then perfectly aligned with each other, including the controller and the control sequence. This product I mentioned briefly before provides different and flexible operating modes. I would like to show you this one here on the next slide. It's for individual seasonal requirements. Here in the first mode, in the standard mode, so to say, you have an aligned cooling and heating mode for heating and cooling capacity matching. What does it mean? If you look at this balance, you have this blue block. This is your refrigeration energy or your cooling capacity, so to say, and the balance of each system means that the cooling capacity plus the amount of driving power for the compressor, this sum basically then gets you the heating energy of the hot side of the systems. So basically this orange block is the intermediate capacity, and then you're adding the driving power of the high stage compressor, and this provides you with your heating energy. In this mode, this is linked, this is firmly linked. So depending on your temperature requirements, you can either say, I have a specific heating capacity requirement, and then you have to provide the resulting cooling capacity with your heat source, or vice versa. You say you have a specific amount of cooling energy available, and I have a specific temperature requirement, and then if you have that blue amount available fixed, then basically you need to consume, or you need to take what you're automatically receiving on the hot side. Otherwise it doesn't work. However, with this system, we are able, for example, to go in a second mode where no heating capacity is required. So this means you can only operate the chiller and switch off the heat pump stage. Then you're still getting the heating energy from the chiller stage, but unlike in this first mode where all this orange intermediate capacity is injected into the heat pump stage, here we don't have that requirement. So the product is prepared that this waste energy, in this case, is dissipated through a secondary external condensation system. So you can add or you can attach a secondary condenser to the system. It's not part of this fusion product, but of course we as GEA have the possibility to help you with this, with our contracting. And then you can have basically this, you can have the product and also operate as a pure chiller if you don't need heating capacity, for example, in the summer season, if your heating is related to facility heating, which you might not need in summer times. Finally, there's a mix between the both of two. If you need less heating required, or if you need less heating capacity, then you would theoretically be able to receive based on your temperatures and on your cooling capacity. Then you can, so to say, regulate your heat pump stage. It looks like this. Yeah, the heating capacity is less than as if it would be possible if you look at the first mode. And this surplus of intermediate capacity of this heating capacity from the chiller stage, there's a surplus which is not necessary for the heat pump stage. And there you can reject this through the secondary condensing system. So basically you have a parallel use for this intermediate capacity. Now the part that is needed for the heat pump goes into the heat pump, and the part that is not needed goes through this secondary external condensation system. Yeah, time to wrap up a few key highlights of our heat pumps. Some of the features and benefits summarized. First of all, the applicability. It's suited for many, many applications. Our heat pumps, there's process heating for all kinds of industries. You can have the facility heating demands for all kinds of communities. The heat source that our heat pumps are using can be handled with all common liquids. It just doesn't have to be non-corrosive water. It can be glycols or even corrosive water, you name it. The minimum outlet of this liquid heat source would be -10 degrees Celsius. So that's actually a very useful temperature for low temperature cooling requirements or for any air conditioning requirements. So basically our heat pump can do air conditioning as well. The maximum inlet is +60. So if on the other hand, you have very, very warm liquid heat sources, the warmer your heat source is, the more efficient your heat pump becomes. So also in this respect, our heat pumps are one of the most flexible here on the market with ammonia. +60 degrees Celsius is a very high temperature that can be used. You can also use direct ammonia gas from an existing refrigeration installation, and that is also possible up to a temperature of +60 degrees Celsius. On the heat sink side, you also can work with any common liquids, glycols, water, and the maximum supply temperature is +59. The heating rating, we've seen that in the chart, starts from a few hundred kilowatts and goes up to 10 megawatt with 1 unit. And the next big important feature is efficiency, one of the most important aspects ever. Market leading efficiency, we do have low energy consumption leading, or that's actually your benefit from the advantage or from the feature of a high efficient product. Why? We have specifically our reciprocating compressors are high efficient because they allow high discharge temperatures. They don't need that water head cylinder cooling that you mostly see. We managed to go without it, and that significantly pushes up the efficiency of that single component. Then I mentioned the heat exchangers that are project individually configured. So that means we're looking at the very precise requirements of a single project, and then we configure the heat exchanger, the sizing, the plates. We add a desuperheater and a subcooler. It's optional. We can remove it, but depending on some requirements, it's very, very energy efficient to include desuperheater and subcoolers. And the way you set this up, you arrange this. So this is a very, very strong know-how and experience point for us. And then the controller, which is also our very own product, the GEA Omni. Again, we have many, many experiences with control technologies and intelligent controllers. They're including smart energy management. This, of course, also contributes to the overall efficiency of the system. And reliability is an important factor. Our heat pumps are based on proven concepts. They're based on the established GEA Blue chiller design. Of course, we're using the high pressure components. Each unit has a 5-step safety chain, so to say, included against excess pressure. There are more on top of the established chiller design. There are more specific heat pump application features to increase the safety, for example, to prevent condensation in the compressor because of low machine room temperatures and high suction and evaporation temperatures, and so on. Again, the Omni control is very important also for the reliability. It includes the predictive maintenance functions. It includes a lot of experience from hundreds of heat pump installations in the past 10 to 15 years. And then finally, it all ends up to the sustainability. That's really the topic of our times, of our generation. Future-proof solution, because it's based on electric-driven devices only. They allow you for an ecologic, an economic, and now looking at the present crisis, also under geopolitical aspects, you need to be, or we want to be, become independent from fossil fuels. High efficiency, safe resources, so it avoids, or depending on the electricity mix, significantly reduces CO2 emissions. You still have CO2 emissions, of course, if you're using electricity that is not entirely based on regenerative sources. So, and the ammonia, it's not affected by any regulations. It's climate neutral, so to say. So that is, of course, also an important factor for the sustainability and the future-proof solutions that you want to have. I'm basically at the end of most of the contents, but I would like to show you 2 more slides. And in the last chapter about project references, we have about 100. I'm not entirely sure. I've missed a few items probably from 10 or 15 years ago, but we are somewhere between or close to 150 heat pump installations, mostly in Europe. And a typical, this is, again, you've seen this in the beginning, the typical classic layout of old factories, not only old factories, still existing factories with air conditioning, refrigeration devices, and the classic boiler. And this is an example now from a beverage industry, but it's very typical. Yeah, food, beverage, dairy industries. What happens here in this case, we have a smoothie production, and there are fruits. They come in, and they're a little bit deep frozen at minus 15 degrees Celsius. So the first heating demand that such a factory has is to defrost the incoming products, and they have kind of like a conveyor belt or whatsoever, and then they have a box where they heat it up to, or where it's about plus 60 degrees Celsius hot, and then it's kind of squeezed and pressed for the juice. And the second heating demand they have is for the cooking or the mixing of the juices, and they have hot cleaning water, so they need plus 85 degrees Celsius on their heating or cooking lines here and for the heating water. Then room climatization, so plus 18 degrees, 16 plus 18 degrees Celsius, air conditioning devices. And then the filled product, they're also in the factory, they're filling the juice, the smoothies into the bottles, and they're storing it. So they have a storage room included or attached to the factory. And this is running at very low plus degrees, yeah, like in your fridge, plus 4 degrees Celsius, for example. Yeah? So, and this is how it looked like. This is how it looked like in the past. And yeah, if factories want to be on the track to net zero, then they're replacing the boiler by a heat pump. In this case, we were able to use the waste heat from the aircon and the refrigeration system. It goes directly into the heat pump, and then the heat pump can provide the capacities and temperatures that that the boiler could also do. Here it's doing it, of course, not just more efficient, also on economic basis, but this location, or there's a specific location. There are several of these factories, but there's a specific location in the Netherlands, and they put on some solar panels on the top, and there's a wind park close to the factory, which they can also hook up to. So this is really a green factory that we have here, because they're now getting the electricity only from their solar panels and from the wind park. So they have really done their homework. They already have their track to net zero. They're already very, very far on this one. The second big application aspect of heat pumps is not process heat, but district heating. And here's a project example from Sweden in the city of Malmö. So this is now communities on their track to net zero. Sorry, this slide is not animated. You see everything at once now, but let me take you through this. At the heat source, they're able to take the sewage water, some wastewater. They're cleaning this, very, very clean, and it's available at plus 14 degrees Celsius, approximately. And then this heat source is injected into 4 very large GEA heat pump units, and it's cooled down. And while doing so, it's cooled down to plus 6 degrees Celsius. And because it's treated, they can put it directly in the Öresund Sea. On the hot side, the return temperature from the heating grid is plus 45 degrees Celsius. And because they have this waste incineration plant there, they're preheating this, or depending on the temperature requirements and the load requirements, they are preheating the heating cycle, the heat carrier, by approximately 5 to 10 degrees Celsius, Kelvin, so that the heat carrier, the hot water is provided for our heat pumps in a temperature range of between 50 and 62 degrees Celsius. And those heat pumps, they do not, they don't lift the temperature that much. They lift it by approximately 10 Kelvin. So after the heat pumps, the hot water is 60 to 70 degrees Celsius warm. And then they're still leading this again through the incineration plant on a higher temperature level. They have waste heat here available to push it up to a usable 75, 90, 95 degrees Celsius. This incineration plant, if this at some point might get switched off or removed or replaced, and we have now the technologies also to do preheating by 10 Kelvin here on the low temperature side. And now, especially with the high efficient piston compressors, we've also seen we can come up to 95 degrees Celsius. So even that step we can now do with heat pumps. And it's not unusual that these projects have a follow-up stage in a couple of years. Actually, this was already done in 2016, 2017. It also received an award, this whole project. The energy company is E.ON. It's not a secret because it's been there's a lot of publicity on this project, so it's possible to read up on this project as well. So it would not be unusual to have a project follow up where also this incineration plant at some point will be replaced, and then further heat pumps do a preheating and post heating of this heat carrier. Yeah, and with this example, I'm at the end of the session. It's already 45 minutes, and thank you so much for your attention. And I believe, I'm not sure if we have questions now, right?
Yes, thank you so much, Thomas. That was very interesting. It's a very special skill to be able to take something so complex and explain it in a simple manner. Maybe you can stop sharing your screen and then I can get to some of the questions. I see we already have 2 questions in the Q&A box, so please send more if you guys have. So the first one, Thomas, is what is the range of volume flow rate and power of the new VXHP series? Someone asked.
Yeah. I don't have the exact numbers, but they are sufficiently precise. The VXHP series, yes, this is one of the new compressors. Piston compressors that are so efficient and go up to 95 degrees Celsius, and they start at 360 cubic meter per hour at a speed of 1,200, I believe, rounds per minute, starting from 350, roughly 340, 350 cubic meter per hour. And the largest one, there are 4 models. So the smallest one has 360 or 350, and the largest one has approximately 950, 960. And the 2 remaining ones in between 500 something and 700 something. So it's kind of like a very, steps in a good proportion. 350, 550, 750, and 950. If you memorize these numbers, you are close enough, definitely. Yeah.
Great. Next one's a bit of a longer one. It's also from an anonymous attendee, and it's asking, is the heat pump industry ready to replace the fluorinated refrigerants with naturals in air-to-air, air-to-water, and ground source heat pumps? What are the limitations of natural refrigerants? Is the use of naturals limited to the size, like propane? And in what type of heat pumps can naturals be used and not be used? A very complex question.
Okay. Maybe I start with the part that I can answer more easily. Natural. Yeah, let's start with ammonia as one of the natural refrigerants that we implement. Our limitation basically, and this has a little bit to do with the design pressure of our components. At the moment we don't have components, or not just our components, but also from the supplier. Above 63 bar is a little bit difficult. So if you take that into account and then you take ammonia as a natural refrigerant, then you end up with temperatures of approximately 95, maybe a little higher, but that's it then. So 95 for higher temperatures. We are still in a bit of an R&D phase. CO2, of course, is also a refrigerant, a natural refrigerant that is popular. That's, or at least in the refrigeration industry, it's used. You need, if you want to use CO2, which is a good refrigerant for heat pump application, you need to go, or you need to, you're entering the transcritical process, and then you need design pressures that are very high, that are at least 100 bar, and we don't have that yet. So with CO2, I'm not so sure. Maybe low temperature heat pumps will be possible with CO2 with our equipment, but on short notice, definitely not temperatures above 95. If you're then using propanes or some freons, which do not have that super low global warming potential, but they're probably not affected by regulations like the F-gas regulation that is gradually phasing out HFCs or even freons. I don't even know what is actually affected. But for some of the harmful refrigerants, the time is ticking, the clock is ticking. And in some regions, they're not allowed anymore, or only in small quantities, or only when you pay a lot of taxes. I don't know, the rules are different. So F-gas regulation is there. So for the remaining refrigerants, to be honest, I'm not familiar with a lot of different refrigerants and how they can be used in what temperature and capacity range. I know that there is R&D activities going on for providing temperatures above 95, which we can reach with ammonia, but it's in a very, very early stage. So I know this probably doesn't answer all the aspects in the question, but if, of course, we get the contact, then I can delegate this to a person who is much more knowledgeable in terms of applications and refrigerants.
Thanks, Thomas. Yeah, it was a very complex question. I think this heat pumps is also such a fast-moving industry now. There's so many exciting new technologies coming abroad quickly.
But I forgot. Sorry, maybe I can add this one. But yeah, with heat pumps, of course, we see when we go when we want to go in the market with our heat pump, we see two things. The first group of customers that also have experience in the refrigeration industry. They don't have problems, of course, with ammonia or any of these refrigerants. They know this. But then there are these guys who are previously just familiar with putting up a boiler and then striking a match or lighting a lighter. This is, of course, quite easy. And then a heat pump is more complex than a boiler. It is true. It's better in a lot of ways. But it is, from an installation point of view, of course, it's more complex. And then you see the discussion about which type of refrigerant, and then you have to convince people of the one type or not. So this is a bit different. But if you talk to people who have experience in the refrigeration industry, then then they're absolutely ready for the natural refrigerants. A lot of people want to use ammonia, but sometimes they have to convince their customers or their consumers about it.
I think it's also a completely different landscape if you look at like residential domestic units versus the larger ones. I think it becomes a bit easier to motivate. We have a question here that was answered in the chat box, but just so for the other people to know, there was a question about if they can get the slides in PDF. We will be sending out the slides this week, and all the live stream videos will be available on YouTube. So all participants will get all the information. So then I've got a few more questions here for you, Thomas. Where do you see your heat pump technologies playing a key role in today's current crisis and concerns with the fossil fuel-based energy supply? You did briefly talk about that before, but maybe you can elaborate.
Yeah, we are working, for example, on, of course, this becomes more significant now. We started in the early 2000s, basically. The first real industrial heat pump was supplied in 2006, I remember. It was a little bit before I started, but that's one of the big projects. And then in 2009, 2010, I actually started in the design department doing a lot of larger heat pumps for district heating projects. So this has been ongoing ever since, but on a low volume until maybe 2-3 years ago. There was a European election. It all became more stricter and more relevant. A lot of governments have their fixed plans, and not just governments, but of course then the industries and the communities. Even we at GEA, we are saying, okay, we have our plan or the idea, the ambition to become carbon-free by 2040. And when previously people were interesting, they were maybe more the early adopters, so to say. They were interesting in how this heat pump works, and if they can even save money, if they smartly connect refrigeration and heating devices, irrespective of any CO2 taxes that are now coming up. So, and yes, those early adopters, they did this, and they could already save money. They were a lot more efficient. And when they called us, or when they were talking about projects, you would be asking a lot of technical questions, but also economic questions, payoff, and so on and so on. What you find now, since for about 2 years, since 2 years ago, maybe. The only question, or the dominant question, is how much CO2 am I able to be? Can I save? This is really, they don't ask about prices often anymore. They don't really are not concerned about other techniques. They ask you how much CO2 can be saved. Done, because they have their plans when they need to save how much CO2. And in certain application ranges, up to 100 degrees Celsius, if we're talking about heating capacities up to maybe several megawatts, then heat pumps are then just a key technology. They're the key technology to replace those systems. And now since that war started, this is even more urgent for a lot of consumers and for a lot of customers. At the moment, we are in negotiations with a client in the Baltic states, and they're calling me and say, hey, listen, we got to have this next winter. We can't get the gas anymore. So of course, heat pumps replacing heating systems running on oil or on gas, and heat pumps running on electricity, and the electricity is more, or the electricity market is a little bit more liberalized than the one for oil and gas. Of course. And finally, it's not only discussed under ecologic aspects, but now also under political and geopolitical independent aspects. So this has become dramatically important now. And we are just struggling with long lead times at the moment because of the supply chain situation. The global supply chain situation is difficult. So if it wasn't for longer lead times, we would be throwing out the heat pumps like the bakery does.
It is so promising to hear that the narrative has actually changed and people have realized that this is the direction that we really have to move into. But I think everyone is struggling with the supply chain challenges. But hopefully at least we're moving in the right direction. Cognizant of the time, just maybe one more quick one before we finish off. You mentioned that you have around 130 installations in Europe. Are you considering expansion into Asia and the Americas as well? Or are you focusing mainly in Europe now? What's happening in terms of other regions?
It's just we are not, our portfolio is basically not restricted to any region, so we don't make those restrictions. It was more coming from the market. In Scandinavia, you would see the first projects. They were very early in this respect. And if we're talking about facility heating, then of course this aspect is not so relevant in a lot of regions where they have different climate conditions. And if we're talking about Asia or Africa or these markets, often, of course, they still have a dominant focus on the purchasing costs, on installation costs, and then of course, and then some regions where the gas and the oil is still available and cheap, then they don't have they didn't really see a lot of reasons to become active in this respect. This was more a European thing. It's now happening. We do have now a few heat pumps in Asia and the Middle East, more than for production processes, of course, not heating purposes. The sugar factories, the breweries who need that, dairy, of course. In America, it starts now. We have a factory in York, in Pennsylvania. And I remember 3 years ago, we had colleagues coming over from product management, application management, and engineering. And when we had a heat pump session in the afternoon, this one day, they kind of switched off and said, it's not relevant for us. A few months later, the phones rang and all of a sudden it became relevant. And their learning curve is now a lot steeper than ours. They have recently started also distributing heat pumps in the United States. They're locally built. They're using our compressors from our core factories. But then the complete heat pumps are packaged locally according to different regulations and so on and so on. And they're doing this now, and projects are coming in. Every second day I read an email, hey guys, we have this project and blah, blah, blah. Can we do this? Can we do that? Because we're aligning, of course, our products, our philosophies. So that's starting in different regions of the world. But of course, depending on the purpose, not every region has these purposes, and not every region has also maybe the spending power for the investment there. From a total cost point of view, you should do it now. Yeah, no question. Even so-called low-cost countries should do it now. Yeah, but
that is
takes a bit to convince them sometimes. Yeah.
That is very good advice to end our session on. You should do it now. So with that, Thomas, I thank you for your time and a very great presentation. I'm sure if people have more questions, they can contact you separately. But yeah, I think from our side.
Thank you so much for the organization. I had a lot of fun. Yeah, contact us, and yeah, slides will be available. So that's great.
Yeah. Great. Thanks, everyone. Our next session will be, from Alfa Laval on reliable and highly efficient heat exchangers for ammonia heat pumps.